Okay, so I thought I would start this out by a story of something that happened to me when I was a senior software engineer and I was also managing a network. And we wound up getting penetrated by two different nation states, one at the top end of the month, one at the bottom end of the month. Strange enough, it was actually the same engineer that got us penetrated. I could never convince him that going to places, since we're a defense contractor, there are some places you don't want to go. So the FBI was very understanding for the first time. The second time I called the FBI, there was this moment of pause. Are you trying to win the award for the most hacked small business in America? And my response at the time was, you have that? Which was not the right answer for the FBI. That was unfiltered thoughts. You can read that or not. You've been staring at my name for half an hour. One of the things I want to ask, and I always ask at the beginning of this, how many of you have some sort of secure coding standard, secure programming, penetration, something? Okay, some, yeah. Usually most of the people don't. So this is, I think, our problem. We have a tendency to sort of look at security as one of those things that we really can't sell as a feature, which is, for the most part, true. You can't sell it as a feature. But we also have a tendency to sort of ignore the implications of not putting that into our systems. And so today what we're going to talk about is, one is how we got where we are, and the second thing we're going to talk about is how do we get out of where we are to someplace better. And I mean, while we're on our path, we'll do a couple of exploits, the classic buffer overflow, and then we'll do an exploit that is actually in the Linux kernel up until a couple of years ago. So the most dangerous place on earth is not a war-torn country. It's not Syria. It's not the Korean Peninsula. It's not any place that you would think it is. The most dangerous place on earth today is the internet. We have gone, just in my lifetime, from 300 baud modems with BBSs to now we have cars that drive themselves. We have everything talking to everything. We have all of these heterogeneous systems that really don't need to talk to each other, talking to each other. And what we're finding out in the InfoSec world is that perimeter security is not going to protect you. If it was going to protect you, it would be doing a great job at this point, but it's not. There's too many ways past it. It's too porous. There are easy ways to get beyond the security networks that because we always had this idea that everything inside is trusted, everything outside is untrusted, and that as long as you have your perimeter security, you're good. The problem is it doesn't work out that way. What we're finding out and what's sort of becoming the mainstay is this concept of zero trust environments. And that is, the environment inside your network is every bit as dangerous as the environment outside your network. It's too easy for a phishing exploit to get people into your network, and in this case I had a network that somebody was able to penetrate twice in the same month simply because somebody did something they shouldn't have been doing. The most disturbing part of it, though, is when I was coming up, it was Matthew Broderick. I want to change my grades, I want to play games. Yes, I may have destroyed the world getting into the wrong computer to play the wrong game, but it was mainly about people just hacking into systems. Now it's, and then it migrated from, well, now it's about money. I can get into your bank account, I can get into your financial records, I can get into anything that I need in order to make money off of you. Where we're going now, and probably the most disturbing part of it is, and why all of these linkages and all these systems talking to each other is such a problem, is because we're starting to see hacks going after things like critical infrastructure, going after things like our power grid. So if you've ever looked at how the power grid works, it's all connected. In fact, from the northern hemisphere of the United States and Canada, it's all connected. You take down one power grid, it puts strain on the rest of the power grid. And in this case, we're seeing people going after power grids, and they're not in there to get money, they're in there to destroy equipment, which means, if you can imagine, what would happen if the East Coast went down, which is actually, there's a major power grid, especially New York. What does it do to our financial institutions? How are you going to do your banking when we've taken down, someone has taken down the power grid and it's days or weeks to get the power grid back up? Then you're talking about loss of human life, because hospitals can only run without power for so long. Then there are the things that we are putting, for example, the aircraft are now in the air, they're fully automated, and they're talking to an upstream server all the time. We have cars that drive themselves and are constantly talking to an upstream server. So we have all of these pieces going together, and Elon Musk even admits that's one of his biggest concerns besides the SEC and all the other stuff he's got going on. He's concerned about a fleet-wide hack. It's not unthinkable. In 2007, DHS managed to penetrate a 757. They got into the flight controls just with it sitting on the ground. It wasn't in flight. But they still got in. They should have. Those should have been air-gapped. Those systems should, the systems they came in on and the systems that fly the plane should never have any conversations at all, yet they managed to do it. If you have a breach like that, what you're talking about is having people being able to control aircraft, cars, things that can do serious damage to human beings. So one of the things we find, especially when I talk to CEOs, we tend to have these three lies we tell ourselves really is, we're behind firewalls. Great. Every company that's been breached in the last 10 years had firewalls. That's just the way it is. The firewalls didn't keep them out, and it's not. It'll slow them down, but it won't keep them out. We talk about, well, it's been code reviewed, it's been tested. You know, there is this sort of moment of, well, how could this possibly have happened? Look at all the testing that we're done. The problem is we're not testing it correctly, and we're not code reviewing it correctly. The things you look for in a vulnerability are going to be very different than the things you're going to look for in performance. It's just a different set of patterns that you're going to be looking for. And then, of course, there's the we're too fill in the blank. We're too small, we're too large, we don't have anything anybody wants. The bottom line is everybody's got money, and software scales really well. The same zero-day exploit that I can run against this company is the same I can run against any other company. And once I'm inside, I can do pretty much anything that I want with that company. So let's talk about who the they are that we deal with. First is, it started out as script kiddies back in the 70s and 80s. And you did have some state actors, but now nation states actually have offensive teams that do nothing more than to take an operating system, tear it apart, whether they've got the source code or not, find the vulnerabilities, and create what are known as zero-day exploits. Those are exploits that nobody's seen. We call those equities. So if they find 20 equities and they save them back for a rainy day, and unfortunately, it always seems to be raining because we see a lot of these coming out of nation states. That filters down to the next group, which is the group that are the criminal organizations, which take those, weaponize them, put them out on the dark web or the dark net, whatever it is that you call it. And those become, and if you've ever gone to anything like Dream Markets, you can find an exploit for almost anything, and they're really cheap too. I mean, they're really inexpensive. They're like $300, and if you want to spend more and get support, you could do that. So we take we take what a nation state can give us, which is scale and money, and then that begins to filter down to criminal enterprises, and then that comes down to corporations who, corporate spying now is rampant. Probably one of the most notable, what we call advanced persistent threats, which is somebody who was penetrated for a long time and they didn't know it, was Nortel Networks. And Nortel Networks wound up being penetrated for almost a decade, and they could never figure out why it is they would lose bid after bid after bid to this one particular company. Well, the reason why is they were working with a nation state which penetrated their systems. They were into the email, their bidding strategies, their contracts, everything. They knew everything that was going on in Nortel Networks, and they know exactly how to react to that in the marketplace. So they wound up declaring bankruptcy. So we have companies that are now taking what comes down from the higher levels and have started using it. Oddly enough, insiders are actually still the largest, in terms of just exfiltration of data, insiders are still our biggest threat. I was talking to a gentleman the other day who said that he had engineers take source code out of their environment twice. So that's twice the code base walked out the door, and these were insiders. One of the things we find a lot, though, is the weakest point in security is not just the insiders, but it's also the people who don't patch boxes. Equifax is a perfect example. This was a case of a contractor that they dismissed. We don't need you anymore. He hadn't patched the boxes. So they were penetrated by known vulnerabilities that had been out there for at least a couple of months, and then it was a couple of months after that they find out that they had been penetrated. So in order to talk about software security, we need to talk about what is a critical system. So there's some terminology we're going to use. The first thing is, what's a critical system? Now, we tend to think of critical systems as just simply being the system that we own. It's the thing holding our snowflake, whether it's data or some other capability, but that's what we own. The problem is that it's not just that. So minimally, it's the system itself, but it's anything else that can interact with it. And I actually had personal experience with this one time. I had my wife call me. She had been doing research at a university. It wasn't sketchy. It was a normal university, and suddenly the printer was acting up. So I didn't think anything of it. I came home. The printer wasn't acting correctly, so when I checked her machine, I found that there was all sorts of redirects going out to a proxy server that I later found out was for a nation state. Somebody had run a water holing attack against this university. She went to the university, it came down. It actually wound up installing firmware on the printer because it got out of the sandbox. And when I turned the printer off, all the redirects stopped. Turn it back on, the redirects start right back up again. So somebody had managed to get to a low priority system, which is a printer, to go after a high priority system, which was the data that was on her PC. So one of the things we talk about is attack vectors. Attack vectors are what we do. It's a buffer overflow. It's some sort of a denial of service. And denial of service tends to be things where we're making use, especially in C++, we're making use of undefined behavior. I send you something into your system, you choke on it, the system crashes, you have a denial of service. We also have privilege escalation, which we're going to do today, and then some others are things like SQL injection, which we won't cover today, but if you've ever seen the OWASP top 20, the SQL injection has been at the top of OWASP top 20 for 15 years, and there's sort of this moment of, why can't we solve this problem? And it's because of the bad programming habits that we get into with SQL injection, where you're not validating the data, you're not using stored procedures and things that allow you to filter out bad code. So attack surfaces are really any surface that I can get to. If you're listening on a port, if you've got a website, anything that I can get to from the outside is an attack surface. But attack surfaces are also the inside. How many people have IPC mechanisms because you have multiple processes and you're talking across different processes? Yeah, so if you work in the embedded world, you probably have a lot of that, and they're across the die, which means you're probably using something like sockets. We don't secure those. We don't secure CLIs, for example. So I've worked for companies where we produced hardware, and one of the things we do is we drop a series of CLIs on there to make it easier for the field engineers to be able to access the software, but we do nothing to authenticate what those CLIs. So if I'm inside the wire, if I've gotten to the box, I can use those things. And look, what's the first thing you do when you type a command line interface? Well, it gives you a nice readout of all of the options that you have. And so you go, oh, well, I didn't know that I could go and use this to reset the system, so now I have an instant denial of service. So I picked the title very specifically for this talk because when I talk about your first line of code is the last line of defense, the reality is it is the last line of defense. Every system that we write is going to wind up being on the front lines of this undeclared war that is on our system. So I picked some examples, and I didn't pick them, they're not meant to be hard, they're examples that I picked out of the vulnerability databases that I wanted to be able to tell a story with. So let's start here. What's wrong with this code? And don't raise your hand, just shout it out. How can it be overflowed? It might be null terminated. The problem is, exactly, you're not checking that length. It may be null terminated. Everything may be fine. With the advice we tell everybody is don't use string copy. Okay, I'm not using string copy, I'm using string end copy. The problem is that string end copy has almost the same vulnerabilities as string copy, except that we don't ever talk about it. So in this case, I've sent in a file name with some arbitrary length that may or may not be right, that's going into a buffer that's a fixed size. So this is a classic buffer overflow. The panel on the right actually comes from CERT. The top one is how bad is this vulnerability? The middle box is how likely are you to make it, to do something like this. And the bottom is what are the remediation costs. Now, I don't really always agree with them, but I put what's in there simply because when it makes it for a standard language. So we fix this, standard string. Good, problem solved? Do what? Yeah, see that's the problem. The advice that gets given to people is we'll just use standard string. It makes it all good. Well, you have a couple of problems with that. One is standard string performs very poorly. Anything over on a 64-bit machine, I think it's 24 characters, becomes heap allocated. So if you've got all these heap allocated strings, you're gonna have disastrous performance. But the other thing is you're not doing anything to verify or validate this data. Who sent it to you? How big is the data? What you're doing is just using a buffer in order to hold it, and then you're sending that buffer, you're actually sending the raw string into another function call because that's what it takes. So the simple solution to this is just check the length. It's very simple. That's why I don't really agree that this is medium. This is actually pretty trivial. If you check the length and make sure that that length is appropriate for the buffer, you're done. You've solved the problem. You don't have to change technology. The other problem with using standard string is there's a lot of things you can't do with standard string. If anybody here uses Google V8, so I tend to do JavaScript and C++, so I'm forever sending things back and forth. You cannot use standard string for that. So you're down to, the first thing you may send in a string, the first thing happens is it rips the guts out of it and converts it to something else. Same thing as if you're doing UTF-8 to UTF-32 conversions. You cannot do that with standard string. So getting people out of the habit of using a piece of technology means when they come back to using that, they've sort of forgotten how it is that they should be using this. In this case, it's very simple, just check the length. And this is probably one of the things that gets us the most. If there is one thing that you do nothing else after today is that you verify and validate every piece of data that comes into your system through the external interfaces or wherever we'll talk about trust boundaries here in a little bit, maintain situational awareness on your data. That right there is the biggest problem we face when it comes to our software. How about this one? It's a bit different. So sort of the same deal. The problem is here. I'm taking in something and I'm just static casting it directly into an enumeration. What if that is not in bounds for that enumeration? In C++14 and before, that was an undefined, or basically it's an invalid value. So you're okay with that. Maybe you check it later, so you check it afterwards. The problem is the C++17, that becomes undefined behavior. And undefined behavior is the point at which we talk about denial of service, software crashing, the kinds of things that make you incredibly vulnerable. So the solution to this comes from the language itself. We have strongly typed enumerations. And the reason why we have these is as long as you've got the types correct, once you static cast that in there, it may be out of range. But what you're not going to get because of two's complement is you're not going to get undefined behavior and crash your application. So look at the standard. I've tried reading the standard. I'm not a lawyer. Apparently it's written by one because there is a lot of very dense text there. But I just did a sweep through the standard and I found something on the order of 269 places where we have undefined something. Those are the sharp edges of the language. If you don't know where the sharp edges of the language are, you're going to wind up running into one of those sharp edges at a time you really don't. So I think for the standards committee, there's got to be a way to do something besides 1,500 pages of legalese. There's got to be a way that we can go and do something that gives people the ability to understand this without having to become the language lawyer. How about this one? Yeah, so I'm hearing different variations of the same theme. Standard copy does not allocate memory. Standard copy will just simply take the place you started, the place you're going to want to copy to, and it's just going to copy it. So this is a heap overflow. So I didn't know that until I actually ran across this. And there are some other ones, like I think Translate, there's at least 2 others that have this problem. But you won't know that unless you've really studied what standard copy does, and in this case, standard copy doesn't allocate memory. So the solution for this one is just use back insert. So each time you do a back insert, it's going to wind up allocating the memory it needs, copy everything over, and everything is fine. Probably a little simpler way is just use direct instruction. Just pass it to the constructor and let the standard template libraries do what the standard template libraries do correctly. So one of the things you probably won't see on there, in this case I don't even think it warns you that that's a problem because it doesn't really know it. But warnings are errors. In the same way that pain in our body tells us something is wrong, warnings in our code tell us that something is inconsistent. It may be okay to ignore that warning, but in reality it's probably not going to be okay. So one of the things we need to strive for is eliminating warnings from our code. You're not going to do this overnight. I mean, I've seen products where I've got 1,500 warnings and we're not going to get them out in the next release. But as you begin to get rid of those warnings are there to tell you something, and we need to listen to them. Let's try this one. Why is it going to give me a warning in the while loop? Yeah. When does this loop exit? Exactly. Well, not exactly, but there you go. There's no guarantee that we're ever going to pass a 0 into this, which means this could go on forever and ever and ever, and it just simply keeps going. So there's a couple ways to solve this. One is variadic templates, which I don't know about the rest of you, but I find these a little difficult to read. But this basically does the same thing. One of the other things we can do is braced initializer lists. So using this allows you to ensure that you're only consuming the data that's being passed in. And that leads to the 4th best practice is complexity is the enemy. If you've ever studied metallurgy, especially when it comes to airline crashes, the reason why we have fatigue cracking is because when you put the system under stress, the energy will all begin to coalesce around weaknesses in the metal. The same thing goes on with complexity in our code. When you will find the easy ones, the ones in the non-complex parts of the code, but vulnerabilities within our end bugs, vulnerabilities inside our code will begin to migrate to the complex areas of our code simply because it's hard to reason about those pieces of code. That's where we begin to miss these things. So one of the things we need to do is begin eliminating complexity out of our code. This is the last one. Which part? Yep. So we don't know when that's actually going to be used. So we're passing something in by reference which may not ever get called until after what was being referenced is now out of scope. So simple way to do it is capture by value, make it mutable. In this case, it really doesn't matter. This is a trivial example, which we really don't care if it's not going to return anything. So grow bug bounty hunters. And this is, has anybody ever done bug bounty hunting? You have? Oh, actually a couple of people, excellent. So large companies will create bug bounty programs, and that is you can go and you can earn anywhere from a few $100s to a few thousand by finding a defect in their code. So Apple does it, Microsoft does it. There's a lot of this is penetration testing from the outside. It's especially popular with websites because websites tend to be the most heavily targeted systems that we see in the industry. They're easy prey. So bug bounty hunters, a bug bounty hunter program would simply look like this, is that if you are a developer and you find a vulnerability that is exploitable something you can get from the outside, you wind up getting paid by your company. Now, if it's your bug, okay, you wrote the bug, you find the bug, you fix the bug. It's not something that we wind up getting paid for the same code twice, but a bug bounty hunter program does a couple of things. One is, it teaches you, your engineers, if there's money on the table, your engineers are going to go out and they're going to figure out how to find these kind of vulnerabilities. They'll take training like this, they'll go other places to get training. They will figure out what the patterns are, because one of the things, as you saw in all of these examples, there is a pattern to the way defects get put into our code. They're little tiny mistakes. One of the things that vulnerabilities have, and that being able to breach a company has with airline disasters, we always say in an airline disaster, it's never one thing that brings the jet down. So it's always a series of mistakes. And you have a chain of events that if you break the chain, you avert the disaster. So in software, it's the same thing. There's rarely ever one thing. It's going to be a combination of, I didn't patch a system, I have a 0-day I didn't realize was there, I've got weak security controls around the software that should be protecting my little snowflake. Bug bounty programs are designed, internal programs are designed to teach people how to be able to go and find these, and then when they do find them, they get rewarded for it. So it does a couple things. One is, you will ship with fewer vulnerabilities. The second thing is, you will wind up learning how to do this, so you're going to write fewer vulnerabilities yourself. And then the third thing is, you're going to find more in code reviews. And we'll talk about code reviews in the next session. But in this case, a lot of companies, my advocate when I talk to CEOs, put a $10,000 check on the table. Somebody finds a verifiable exploit that they can be exploited in your code, and they say, well, 10 grand, that's huge. Yes, but the over and under on your stock drop when you do get breached is going to make that look cheap. And yes, unfortunately, most companies do, their stock will recover. So, maybe the CEO gets fired, the CTO gets fired, there are people, but the bug bounty programs begins to bring that in-house. We tend to see a lot of people coming and doing penetration testing from the outside, but nobody that really does a lot of bringing that in-house and those skill sets in-house. So what do I look for when I penetrate a system? The first thing is anytime you copy memory, because you're likely to get it wrong. That first example was a good example of getting it wrong. Anytime you don't validate and verify who you're getting your data from, that is the easiest way to penetrate a system, is me being able to send you information that you're not expecting, you haven't decided, you haven't figured out who I am, so you don't even know if I'm a threat actor or I'm somebody who should be sending you data. You just simply process the data. So denial of services and DDoS, which is dynamic denial of services, are usually where you're getting data from somebody, but you haven't verified that it's somebody that you care about getting data to. Open source libraries, their weaknesses are yours. When you use an open source library, one of the things that I always coach people to do is prefer libraries to where you have the source code and they're going through a continuing set of security checks. So when we get into the next hour, we're going to look at something that was fixed, then it was broken when they went to fix a different bug, and then it got fixed again 9 years later. So what you don't want is to just say, okay, we've blessed this. This is good, because then every time you change the code, you may be introducing some other vulnerability that you don't realize is there. Internal interfaces, IPC interfaces, USB interfaces. If I can get you to let me put something into your system, if I can get you to, if you're expecting that what is inside is safe and what is outside is not, it's not. What is inside is just as dangerous, because once I'm inside, I can now go after anything that I want. And if you're expecting the perimeter security to protect you, it won't. And then again, any place I find complexity in the design, and I'm going to come back to this over and over again, because I see so many times where we have vulnerabilities in code that has nothing to do with people making a mistake. It's just, it is so complex that they wind up not seeing the bug simply because you can't see the forest for the trees. So how many people have ever run a buffer flow exploit? A few people. Everybody, does anybody not know what they are? Because that's what we're going to do. So a buffer overflow exploit, this is sort of where it all began. back in the 90s and the 2000s when people began to find ways to penetrate systems. So this code is actually the same code we used. We saw this just a minute ago. We have a buffer flow exploit. We're using string ncopy. We're passing in a length we're not validating. So there's a couple things we can do with this. One is I can crash the application just by writing a ton of data in there, or I can do something that will be a little more helpful, and that is execute arbitrary code. So this is one of the things we would want to execute. Up there on the top left, this is for a Linux system. I just want to run a shell. You can do the same thing with Windows, you're just going to run a command. Over here on the right-hand side, that's just the assembly code for that. It's just a few registers and then a call. So it's very simple. This is a very trivial piece of code. So here we have the model for an x86. You've got program space on the bottom, the kernel's on the top, the data heap is on the bottom, which grows upwards, the stack is on the top and grows downwards. No matter what memory you're accessing it, you always access it from low to high. So I pulled out a piece of what a stack would look like. So the gold on the right-hand side is the stack frame that's above. And I removed some of the things we don't need. There's actually more in here. The return, that is just when you make a function call, that return value is going to be where the function comes. The next instruction comes when you return from that function call. So every time you create a new stack frame, you need a way to go back to the line of code that called you. So EBP, RPP, that is just the stack frame pointer. And then we have our buffer and loop. So what we have here that's useful to us is the return and the buffer. So we have two pieces that we can play with, and what it would be really nice is instead of that return going back to where it's supposed to go, it'd be nice if I could put it into some place that I control. So what we do is we do what's known as a no-op sled. Now there's a couple of different no-op codes. There's the long version, which nobody uses, and then the short version, which is the hex 90s you see here. What we want to do is we want to take that return and replace it with a return that goes back into our buffer. That's the overflow. We're overflowing the buffer. We don't care about the frame pointer. By the time the frame pointer figures out it's bad, we're going to have, it will be all over. So what we want here is we don't want to have to be precise about this. We want to be able to cover that return code to come somewhere back into our buffer, hit a nice big landing pad, and then have the no-op slide bring it down to our code. So you see this code here, which is what it would look like, what the payload would look like. You see it's got all those hex 90s, that's the slide. Then you get down here to line about 190 and you see some more hex 90s, but then you begin to see some what looks like code. And then a couple lines down you see the same address repeated over and over and over again. What you're trying to do here is you're trying to be able to take that return address and sort of slide it over the top of the return. That return address can be somewhere in your buffer. Hit the no-op slide, go down, execute your code. So we're going to do one. And what we're going to do is we are going to start from a buffer that's in a small buffer. We'll overflow our own stack space, and then we'll overflow into the stack space above it, so the calling function. Does anybody have any questions at this point? Because I'm well ahead of schedule. Go ahead.
Will we get a slide? How can we get a slide?
Watch the video. I'll have to work on the slides. Oh yeah, the videos come out over about a month, yeah.
Your remark about open source libraries or any library is not something specific to open source, right?
Absolutely. So the question was, is that your comment about libraries is true for any library, not just open source. So here's the thing about open source libraries. With an open source library, I get the source code. If I'm going to hack into a system, the thing I want is the source code, because that's where I'm going to go find my vulnerabilities. We'll talk about that in the second talk, because there's this, it's a Linux vulnerability, but it's open source. So one of the things I always want in the source code is I want to go get some idea where I think the vulnerabilities are, and then I can go ahead and start testing around that area and see if I can make something happen. So you're right, it's any library. It's the libraries that I consume, I want to know that they're undergoing periodic security reviews, but I also want to know, I'd like to have the source code so I can look, but it becomes one of those things you do not want libraries that somebody has said, okay, I've put together my library, it's never been reviewed, it's not under ongoing review, so just use it. Because the problem is you don't know where those vulnerabilities are, and because you don't have the source code, you can't find those vulnerabilities. Anybody else? Yeah. Is this what for ASLR? Yeah, so we're going to talk about ASLR here in just a minute. This box has ASLR turned off. And the reason why I turned, so the question was, does this assume ASLR? The reason why I turn ASLR off on this kind, because if I had to do an exploit where ASLR is active, it would take most of an hour just to explain the exploit because it is very complicated and it's not something that's going to fit. You're not going to get it to work the first time. You're going to have to work through some of where the address shifts are, and we'll talk about ASLR here in a minute. Anybody else? Yeah.
So the no-op slide is needed because you don't know the exact place the return is going to take you?
So the question is, the no-op slide is there because you don't know the exact address that you need to hit. The no-op slide is there so I don't have to know the exact address. I can just put it in an area of the code, some index off of where it is, and I don't have to be precise. It makes it much easier to be able to do a buffer overflow. Anybody else? Yeah. Buffer overflows. So the question is, how do you test for buffer overflows? We're going to talk a lot about testing in the second talk, but minimally, you're going to be doing code reviews. So when engineers are young, they go in, they find out that they want to cook their lunch, they find out that the microwave is broken, they pull the microwave apart, they go in, they fix it, they put it back together, cook their lunch, and they go on about their day. Hackers are a little bit different. They go in, the microwave is working just fine. Cook their lunch, and then they sit there watching the microwave thinking, how can I make this microwave do something it's not supposed to? How can I make it blow up? How can I make it do something other than what they expect? It's a different train of thought. We go and we look at how can I take these pieces and how can I build this beautiful algorithm? How can I have this extremely excellent performing data structure? Hackers are, how can I go and I take something that somebody's built and turn it inside out and turn it into a weapon? It's just a very different way of thinking. So when you find these things, when you're looking for these things in source code, what you want to do is you want to begin thinking about, how can I break this? And I know it's hard. I've been doing this for 30 years as a professional, but the bottom line is, I'm not a good tester for my code. I want my tests, I want my code to perform. I'm more about building it. I'm more about it working well. You don't want to find out your baby's ugly and you've dressed it funny. One of the things that you have to begin doing, though, is looking at your code in a different way. How can I break it? What can I send into this code that's going to damage the code or make the code do something that's unexpected? And that's where complexity, when we talk about complexity, we talk about emergent behavior. We have those moments of, oh, I didn't realize that was going to work that way, because it is very complex. So how you view your code, rather than once you've built it up and it's beautiful, it's doing exactly what you want it to do, is how can I destroy it? And so many times we don't get to that part, and that's why these vulnerabilities tend to slip through our testing. But we will talk a lot more about the types of testing we can do in order to be able to catch these things before they go out the door. Yes? I'm sorry, I didn't catch it. We will talk about stack canaries. Somebody's been reading ahead. You're giving away the rest of this part of the talk. Yes, we will talk about stack canaries, and I'll explain how they work. Yes, sir.
Is this still a problem if the stack's not executed?
You guys are reading ahead, great. I'll go ahead and talk to you about countermeasures since everybody's been bringing them up. Okay, so ASLR, address-based layout randomization. What ASLR does is it just randomizes certain places in your address space. So there's a hack called a return to libc. So there's a system function in libc, and if I can know exactly where that system call is, instead of going into my buffer, I just point it back out to where that library starts on that system call. It's the exact same thing. I'm running in the context of whatever this application is running in. I just simply go out, I run it. So randomizing where these things are it makes it much harder, much more of a challenge to hit. So. It's the wrong password. Okay. So I've already got my code. There's no reason for us to compile all of this, but if you look on here, you'll notice that there is a function called vulnerability, or just vuln. So vuln is this is just my code that has got the vulnerability in it. The reason why this is red on a Linux system, for those of you that are not running developers, is because the set UID is set on it. So when you run this, you're gonna run it as root. And there are a lot of things that you can run in Linux, like SU, you can run ping, which is owned by root, so it'll run in the context of root, which is analogous to running things as an administrator on Windows. So I have my shell code, which we looked here. We'll first look at so there's my payload. It looks a little bit different than what we covered, because what I'm going to do is I'm going to overflow that buffer. So my addressing is first. So I'm at the bottom of my buffer. The address is going to point up into the stack frame above me with a nice big buffer and run my payload out of that. The code is very simple. I'm just going to go open the file. I'm going to read in however much data happens to be there. In this case, it's going to be going into that buffer called str. Then I'm going to make my function call. Then it's going to go into bad copy, and that's where the overflow happens. So if we look at my account, I'm just a regular user. The shadow file, for those of you that aren't Linux developers, that's where all the passwords are. I should not be able to view that if I'm just a normal user. So I've run my vulnerability, and now I have this strange hash mark here. So the vulnerability has pulled in the data, it's overflowed the buffer, it's now run my exploit. And now I have root access. So if I want to look at the problem with live coding. I can now see the passwords on the file, which I should not be able to see this. Now that I have root access, I can do anything that I want in this system. So now that we've done this once, let's find out what a failure looks like, because in buffer overflows, so if somebody's trying to run some sort of exploit like this against you, where you're overflowing, whether it's heap or something, you're going to see memory that's going to be corrupted in a very specific way. So I'm going to change my file so that this is a failure. And right now, if you look at bad file, it's 517 characters. So we're going to see now it's 200. This is going to fail. In fact, we want this to fail. So if we run our vulnerability again, we get a core dump. So you have the same analog in Windows. You're going to get some sort of memory dump of the failure. So what I want to look at is at the core file. So made now to dump the core file. Now we have a core file. So now we wind up having a stack that's got 2 stack frames in it. So if we go to frame 1, and we want to see what is in that, it looks pretty normal. It looks like, just like regular memory. There's really nothing there. But that's because we overflowed this buffer, but that's not where we put the payload. This was a small buffer in one. We actually overflowed into the stack frame above it. So let's go look at that one. Now all of a sudden we begin to see at the top, we've got what looks like a repeating address. We've got a bunch of hex 90s. We've got other things. These are sort of the telltale marks that when you have a piece of code that has been running just fine in production, it suddenly begins failing for no explainable reason. Go and look at the memory. Go and look at, when you have a crash, go look at the stack dumps. Go look at the memory dumps. If you begin seeing strange behavior like this where you've got tons of, you'll see hex 90s. That's, I mean, we have no ops in there and it's mainly used for padding. But if you begin seeing this kind of behavior, what it means is somebody is trying to, whether it's successful or not, they're trying to run something against your system and it tells you somebody's out there. Also tells you have a bug. So I always tell people all vulnerabilities are bugs, but not all bugs are vulnerabilities. You can have these things fail for reasons that have nothing to do with someone penetrating it, but at least it gives you a clue as to where you're going, why you're having this particular problem. So let's talk about some of the countermeasures, and these countermeasures came into effect in the early 2000s. Every operating system has them. Address space layout randomization, what we're doing is the stack and the heap are basically where they normally are, but we're moving programs around, we're moving libraries around. This, the libc attack where I want to call system, if the library code is moving around, I suddenly don't have a reliable place to find it. Now there are ways you can get around this. Address spills are one particular way of getting around it. You can also try brute forcing it just by going through a range of places. It becomes worse on a 64-bit machine because the address space is enormous compared to 32-bit. But what these do is these change where things are located so that you can't get to them easily. And this is handled by the OS. So this isn't anything you can do. Now, the one thing you can do is you can, believe it or not, you can turn this off. And I've seen people, they didn't really realize what ASLR was, so they turned it off because they thought it was going to give them a performance boost. It will not give you a performance boost by turning it off. It doesn't. You're not paying a penalty for it. One of the other ones is stack canaries. Somebody brought up what a stack canary is. So we started doing these ourselves, which is I just put some known bit pattern right below the address. So the EBP, RPP would be right above the canary, and I took that out to make it easier to see, but I'm going to write some known bit pattern in there. Then right before I do a return, I'm going to go find out if that bit pattern has changed. If it has, somebody's overflowed the buffer. And then I abort at that point. In fact, that's what a lot of these will do, is if they find these things, they will abort. It is turned on by default in every compiler, so make sure somebody didn't accidentally put in the wrong compiler flag and go and turn this off, because it is useful. It is also not foolproof. There are ways to brute force it, there are ways to guess it, there's a million ways to get around it. This is an arms race. I mean, we come up with things to protect the system, somebody's going to come up with a way to penetrate the system. So, questions? Yeah.
Do you use tools like, or recommend tools like, sanitizer?
Yes, in fact, the entire next talk is going to be around things. So the question is, do you recommend tools like sanitizers? And absolutely. We'll talk about some of the best ones out there and when to use them. So there is, I have a tendency to hear people say, oh, well, you know, I just use static analyzers and it's all good. I mean, the static analyzer is going to catch everything. The static analyzers are not going to catch everything. Static analyzers are good for what they do, but they are not good for everything. And so we'll go through all of the different things that we can use to test our systems to make sure that when that system goes out the door, we have gotten vulnerabilities. And we'll do things like threat modeling, and we'll do a quick exercise on that. Yes?
So can you explain the difference between the one that you use versus the one
Okay, so what happened was when I did it correctly, I had an actual address that went back to a region. So when it tried to go back to that, it found executable code in there. In this case, it was a bunch of hex 90s. The one that failed, though, is I overflowed the buffer. I blew away the address, but I didn't put a valid address in it, and the system recognized it. And so it crashed. You'll get the same kind of core dumps if you have ASLR turned on and if you've got stack canaries in place. When it finds that there's a problem and somebody's been playing with the cat, it's just going to abort at that point in time, so you would a core dump there too. Yep, right here.
You covered at overflow attacks. How big of an arsenal of attacks are there?
So the question.
Is it infinite, or is there like a number that?
So the question was, how big is the arsenal of attacks? We're really creative people. We can find ways to get into almost anything. What it does is, we find out that there's an attack of a particular vulnerability, we patch it, they come back, they look for a different way in. There's no bounds. And here's the thing, a lot of people will say, well, yeah, I mean, once you've sort of figured these out, the problem is that the technology keeps changing. And you wind up having, we write new exploitable code every day. So in that end, there are classes. So buffer overflows are one particular class. Then there's code pointer exploits. Then there's SQL injection. Then there's what we're going to do here at the end of the next talk, which is going to be something quite a bit different. And there's nothing in the OS that will protect you from that. That's just code that misbehaves that I can take advantage of. So in terms of what they are is there a discrete number of patterns. So if you get used to seeing the particular patterns of how code gets exploited, you'll know how not to write exploitable code. But in terms of the arsenal, it's infinite because we're just really, really creative people. I think I had someone over here.
So in your example, if the S-bit had not been set, it would still have started a shell before it contributed.
Yeah, exactly. The reason, so the question is that if the set UID bit had not been set, then you're just running in the context of your own account. You haven't really gained anything because you're already in there on that account. The reason why, and I have actually a slide that deals with this, in Linux and Windows, you will have pieces of the operating system that are running as a high privileged account, which is why we call this a privilege escalation. We're getting extra privileges by taking advantage of a vulnerability. So in the case of this one, it's running as root, and there are things like ping that will run as root, and that's the way the operating system is designed. There's things in Windows that will run as system, or things that will run as an elevated privilege because they're autonomic to the operating system and they need those privileges. It used to be much worse in Windows because back before Windows 7, everything was an administrator, and so it was really easy to take advantage of privilege escalation because everything ran as an escalated privilege. Question? Anybody else? Yeah.
You've seen a lot of return-oriented programming, or has that kind of quiet again?
So the question was, how do I see a lot of return-oriented programming, which is, this is actually a case of return-oriented programming. He's talking about a class of vulnerabilities that I just talked about earlier. Are we seeing it? Yes, and we're getting really creative because it's died down in that the easy stuff is gone. What we're still seeing though is that people are finding other ways to get around ASLR. They're finding ways, so you can do code pointer exploits. Well, if that's on the heap, then that's not covered by a stack that can't execute code out of. So there is still a class of that. What we're seeing more of a rise of at this point is we're seeing more phishing exploits where you're already inside the wire, you're making use of a vulnerability that no one knew was there. So this is sort of becoming a class that sort of is getting smaller, but it's still there. Because especially if you have things like an address spill. If you tell me where the address is, either because it's in your logs or because you've made a mistake, well, now I can run that whole class again against your code simply because I know where the beginning of the libc is. And I can know where, now I know where system is, and now I can feed you the same data, except instead of having to execute something on the stack, I'm just going off to a different place that's not on your stack. Anybody else? The what that I'm talking about? Oh, the stack canaries? Stack canaries are created by the compiler, so you don't have to worry about creating your own. You can if you want, but it's redundant. We started creating stack canaries back in the early or late 1990s and early 2000s as a defense against this until the compiler vendors began to catch up, and that's when they put in ASLR, they put in stack canaries, they put in, and these are all progressions. These were not, one day we woke up and said, okay, here's the 3 technologies that are going to fix this. What we do is we'd add one and they get around it. We'd add another, they get around it. We'd add a third, they get around it. So what we've talked about, whether it's stack canaries or ASLR, is we've made it more of a challenge to do it, but we haven't eliminated it completely. It's just, and then the other part of that is we found easier exploits. The one we'll do at the end of the next talk is actually really simple. In fact, it will take me longer to explain it to you in a way that everybody can consume it than it will be to actually run it or code it up. Anybody else? Oh, yeah, sorry.
In your experience, are there any safer compilers and platforms?
Chandler Cruz is sitting here. I love Clang. Compiler vendors do an excellent job. Most of the difference between compiler vendors is how they optimize code. We have not really found a lot of exploits that come from, oh, well, I wrote the code this way, the compiler exploited it, they optimized it this way, which generated the exploit. So the compiler vendors are really good about making sure that they're not creating exploitable moments. And the other thing we're doing as far as the language is concerned is, if anybody is familiar with the standards, SG12 is there to look at each proposal that comes through and say, where are we creating potential vulnerabilities in the code? Where are we creating these sharp edges that we talked about? So we have undefined behavior and trying to get those out. And then going back and looking at old code and saying, can we modify this? Or at least going and look at the standard. Can we change the standard so this becomes something that is not undefined behavior? And Chandler did a really great talk a few years ago on undefined behavior, and I think his point was well taken, is we need to start removing undefined behavior from life. We need to come to a point where we can define the behavior for it. It may not be correct behavior for the context of the application, but at least we need to be able to define the behavior. Anybody else? Yeah.
What about things like fuzz testing and stuff like that, just sort of more and might work, might not find anything more?
Yeah, so fuzz testing is actually a good way to do this, and we will talk more about fuzz testing in the second half of this, because what I wanted to do, what I did with the talk is, I split it up. I want to know, okay, how do we get to where we are right now? And then the next talk is going to be, what do we do about it? And that's going to include a lot of things like threat modeling, testing, another group of best practices of things that you can do that will eliminate these problems in your code.
Especially Linux is like Kali, which kind of builds itself as a security-oriented Linux. Do you have any experience with that?
So the question is, do I have any experience with specialty versions of Linux, for example, one that Kali that says that it is a security. I don't spend a lot of time thinking about whether or not this particular implementation is safer than that implementation, because a lot of the really worst exploits, and the one we're going to do, is actually built into the kernel. So unless they're rewriting kernel code and we don't know about it, they're using the same kernel that every other one is using, so they've got the same liabilities that every kernel has. In fact, the exploit in the next talk is one that hit every single implementation of Linux out there, including Android. So are there some, there's like Backtrack Linux, which is actually a really good Linux that you can use in order to be able to go and actually do penetration testing, and it's got all sorts of tools built into it. Theoretically, that's safer. But I wouldn't go with a distro simply because they advertise that it's safer unless it's demonstrably provable that they are safer. Okay. Probably have time for one more question. Okay, let's take a break. We'll come back for the second half. Thank you.